Okay, this is part 284C3M1b7C8E13C9C6D3P38D19D6. No, D6C. There we go. Sorry, got it mixed up there. Line 22f1fa19c3m 1b7c8e13c9c6d 3p38d19d6c. Hertzian Dipole Entropy 5G Wow Seti. And this is the alien radio signal. And this is keyword research entropy production rates from Hertzian Dipole from the WOW data. It's supposed to be lambda. I goofed. Sorry. March 9, 2013, keywords Hertzian Dipole continues from the previous videos. Line 22, F1FA, 19C3M, 1B7, C8E, 13C9, C6D, 3P, 38D1, or D19D1, sorry. Hertzian Dipole loop patterns 5G Wow Seti. The formulas from the data were found in this video and the previous video. Line 22, F1FA, 19C3M, 1B7C8E, 13C9C6D, 3P38D, 19D2, Hertzian Dipole Magnet Transformer 5G Wow Seti. To line 22, F1FA, 19C3M, 1B7C8E, 13C9C6D, 3P38D, 19D5. Hertzian Dipole Antenna Formula 5G Wow Seti, and then from that I got the dissipation, lambda, and ferrite rod, and then we had dissipation water engineering from this video, line 22, F1FA, 19C3M, 1B7C8E, 13C9, C6D, 3P, 38D, 19D6B, Hertzian Dipole Dissipation Formula 5G Wow Seti, which brings us to entropy production and Riprap, which were two of the keywords that were found in under the water engineering data on Wiki. So my thoughts, two-dimensional gas might already be covered here in WOW data. We're going to cross-reference that at lines 1 to 22, and there's 28 videos so far. So we're going to wait until line 27 is done to finish our cross-referencing project for those keywords. So the keyword Hertzian Dipole to entropy production is quote from Wiki. Entropy production determines the performance of thermal machines such as power plants, heat engines, refrigerators, heat pumps, and air conditioners. It also plays a key role in the thermodynamics of irreversible processes. Clausius gives the expression for the entropy production for a closed system, which he denotes by N in equation 71, which reads N equals S. Well, there's the equation there. I don't know how to read it. Here, S is the entropy in the final state, and the integral is to be taken from the initial state to the final state. From the context, it is clear that N equals 0 if the process is reversible, and N is greater than 0 in the case of an irreversible process. Here's another diagram here. And this is general representation of an inhomogeneous system that consists of a number of subsystems. The interaction of the system with the surroundings is through exchange of heat and other forms of energy, flow of matter, and changes of shape. The internal interactions between the various subsystems are of a familiar nature and lead to entropy production. Examples of irreversible processes. Entropy is produced in irreversible processes. Some important irreversible processes are heat flow through a thermal resistance, fluid flow through a flow resistance, such as in the Joule expansion or the Joule-Thomson effect, diffusion, chemical reactions, Joule heating, friction between solid surfaces. The expression for the rate of entropy to production in the first two cases will be derived in separate sections. So we have a heat engine, and then we have a refrigerator. A schematic diagram of a heat engine, a heating power. QH enters the engine at the high temperature of TH, and QA is released at ambient temperature TA. A power P is produced, and the entropy production rate is S to the power I, or down, no, not power of, little, oh, I don't know how to say that. Schematic diagram of a refrigerator is Q with the little L, is the cooling power at the temperature T, little l, and Q, little a, is released at ambient temperature. The power P is supplied, and S with the little I is the entropy production rate. The arrows define the positive directions of the flows of heat and power in the two cases. They are positive under normal operating conditions. The keyword in the next video should be, what do we got here? Riprap. Yeah. It's going to be Riprap. So I missed that somehow. Thanks for watching.